Braincast, der Schulfunk zum Gehirn.
So I guess we should emphasize that we are not just talking about animals here, or that we're talking about all animals, including humans. And that's an evolutionary process that includes fear and anger and
seeking
primary emotions in every mammal vertebrate.
But as you go down into cold-blooded vertebrates, they do not show maternal care, many of them. So we are mammals because we're dependent on each other. A sea turtle comes to a beach and it lays 100 eggs. And then the little ones have to be nurtured by the sun, warmed and hatched. They come out to the world, they run to the sea without maternal care. All mammals need mothers, and mothers have to have the principle of care. And we call this system capital C-A-R-E. So there's a care system. Now that also shows learning, it shows thought. We have not focused on those higher levels because our fundamental point of view is you have to have a clear image of the foundation of mind. And that's the whole project of my kind of affective neuroscience, the original form. Now many people are using brain imaging and seeing higher cortical areas light up. That's wonderful research, but it rarely can see the primary process. It's sort of like the Galileo's telescope could see the horizon and a ship coming up from the horizon. Then we had better and better telescopes. Finally, Galileo could see the planets and the moon in detail. So we were beginning to see more and more complexity that was more and more recent. Now we have the Hubble telescope and we can see millions of years into the past. The light is just arriving from millions of years ago. It's the same problem in neuroscience. It's very difficult to envision the primitive parts of the brain because they are so powerful. They have been around for such a long time that they are not sensitive to changes, small changes in metabolism that the brain imaging can sense. So we're getting a good image of the recent brain, but a very poor image of the ancient brain. Mm-hmm. Very often the ancient brain is not operating by cells just firing more rapidly. It's the pattern of the firing and what chemistries are released. A change in the pattern can change the release of chemistry, but if it's just a change in pattern, you will never pick it up on the modern brain imaging. So you have to use different techniques, and that is, I think, one of the great problems right now in bringing this animal data to the forefront of thinking about our own nature. But I think all those systems are inside our brains. So if you asked a smart neuroscientist that was perhaps the devil's assistant, and they would say, you will lose 10 grams of your brain. You don't have a choice about that. But you have a choice about which part of the brain you will lose. You better understand your systems. Anyone that says, I'll lose 10 grams right in the middle is an idiot.
Yeah. Inside the ventricular system.
Yeah. 10 grams over here, no problem. There was a musician that had a frontal stroke. And he said after the frontal stroke, music has much more emotional power. Mm-hmm. And he said, if I could have another stroke that gave me as much pleasure in music as the first one did, I would be happy to have it.
Okay, we talked about seeking system and the care system. Are there others?
Yes. First of all, the care system depends heavily on the seeking system. Okay? All the emotional systems are talking to each other. But The most primitive systems that all vertebrates have are rage, the way Walter Hess discovered. We can make reptiles angry and aggressive. They all have a fear system, and the most important part is under the amygdala. Most people say, amygdala is the heart of emotions. That's not true. It connects it to learning, which is important. They all have a seeking system. So those three primitive systems every vertebrate has. But mammals, and maybe some alligators that take care of their babies in their mouth, but all mammals have a care system. It's stronger in females than males. It's a biological difference. We also, all the vertebrates have a lust system, sexual system. So those are the primitive social systems: lust, sexuality, and care. An evolutionary understanding of the brain indicates that the maternal care system grew out of the lust system. It has to come from somewhere. And when you already have social pleasure of a reproductive sort, why not use the chemistries not only for attaching to the pleasure of sex, but to the pleasure of a social relationship? So the chemistries of lust were modified and used for the chemistry of care. So it's a more subtle system. And then we really become more subtle. And the two systems that we mapped almost completely by ourselves are the last two. So there's primitive rage, fear, seeking, lust, all capitalized. Reptilian, every vertebrate. Then we have maternal. Now you're in the mammalian realm. We also produce babies that are so immature that we have to take care of them, but they also have to indicate to us that they need us, because they can't survive without us. So we have a love between mother and child and mother, the primal social bond that has to be of high quality if the child is to grow up psychologically normal. Without a mother, a child cannot survive, and if they just have nutrition, it's not enough to nourish the mind. So they need a positive social interaction, and the primitive way for the young one to indicate their psychological need is to cry out when they're lonely, when they're lost. So there's a separation call. That little puppy show, guinea pigs, pretty much every mammal except the artificial mammals that we produced in the laboratory, like laboratory rats and mice. The behaviorists wanted animals that would live alone in a cage, and they probably selected animals that could do that because they didn't feel the pain of loss. So that's a real problem in science, and for that reason we did not do that kind of work in rats and mice. But even a little chicken needs mother, and we mapped this separation cry, and we think that is the foundation for love between mother and child. We think it's also the foundation of the social bond. And it turns out that one of the powerful chemistries that produces this good feeling are the brain opioids. And we demonstrated that in the mid-1970s, and we shared an important story about addiction, that opiate addiction is fundamentally built upon the capacity of these brain molecules to reduce psychological pain. And that the reason people get addicted to opiates is because they don't have enough social satisfaction in their life. They are feeling lonely inside, they're feeling psychological pain, and they discover that a molecule in the world can reduce that pain. And gradually, because of the chemical dynamics, they become addicted to it. Just the way a mother becomes addicted to the child, and the child becomes addicted to the mother. There's other chemistries, oxytocin, prolactin, many chemistries that haven't been identified yet. But this social principle percolates throughout society. We know that one of the main sources of depression is too much psychological pain. Mm-hmm. So right now we're working with the idea, if we understand the chemistries of these systems, we might have brand new antidepressants, because we can alleviate the pain of loss, the pain of depression.
If I'm correctly informed, you already have some molecules in mind to fit in there?
When we think about depression and we say the gateway to depression is the pain of losing people you love, it's a very simple idea. We identified the brain system that is active and causes the psychological pain. We worked out the chemistries that are able to suppress this system. The most powerful chemistry was safe opioids.
Safe opioids.
Safe opioids. Opioids that are impossible to get strongly addicted to, because they have a biochemical property that works like morphine and heroin at the low doses, but then it changes to blocking the system. Okay? So they've got two faces. It's like a Janus-faced molecule. On the low side, it's good and smiling, and on the high side, it turns to the opposite. So you cannot get addicted to these molecules, and our thesis is that these molecules would be wonderful antidepressants. Mm-hmm. We have tried to get a proper scientific trial going in America. It's very difficult, because if these old molecules that have been around for a long time are more effective than our SSRIs, the ones that aren't very good, but they're very safe, then I think people would begin to lose money on them, pharmaceutical companies. And if it's an old molecule that's off patent, there's not a desire from the economic side to support them. But our feeling as scientists is that we would like to have the proper studies done. We've had plenty of experience with open trials, that yes, it works, and many people that have failed every medication. And for instance, in Germany, Austria, these medications are available for patients to treat themselves when they have breakthrough cancer pain. So there's very tiny doses that people can control their physical pain. These tiny doses, incredibly tiny doses, look like they would be effective antidepressants. And the molecule is buprenorphine. And on top of that, it has another biological property, which is that it reduces the effect of a negative feeling chemical system. Like when we do studies on animals of depression, one chemistry that becomes very strong gradually as a consequence of stress is a molecule called dynorphin, which is one of the strongest opioids in the brain and very widespread, but it feels bad. Dynorphin becomes stronger during depression. Everyone is looking for a dynorphin blocker. They have plenty of them, but they're very sticky in the brain. You take one, it lingers in the brain for a month. It turns out that buprenorphine is the only molecule that's already available that's a good kappa antagonist. Mm-hmm. So this molecule can increase positive feelings and suppress negative feelings. So with affective neuroscience, we're finally taking the approach that it's not just molecules and labels on people like depression and anxiety, that in between the brain and molecules, there are large systems that control emotional feelings. And if we understand these feelings in animals, we should have many new ideas on how to treat people. Specifically, modifying the mood states so they can reestablish a feeling of normality. And buprenorphine is one, and we do have another molecule that has come from this kind of thinking that just went into clinical trials. At Northwestern University, a group of scientists that I'm part of, that's the Falk Center for Molecular Therapeutics, they were doing brain cancer medications. They invited me when I retired from my university to come develop an affective neuroscience program. And that program now has discovered happy molecules because we know where the happy circuits are, because play is the happiest thing there is. And we know that animals laugh, at least rats, and we can study that like a biochemical assay. The output is laughter, but we have the animals in a very controlled, tickling situation.
Okay, you just mentioned play. This was the thing that surprised me most in your system. Mm-hmm. I didn't find it anywhere else in any other psychological emotion system. Where did you get that from? How did you get the idea to tickle rats?
Well, we were studying play for 20 years before we ever had the idea of tickling a rat. When we had gotten a basic understanding of psychological pain, separation distress, the source of loneliness and grief to depression, we said, now let us study the opposite side. It's like in a theater, you have two masks. One is crying and one is happy. So we wanted to study the mask of happiness and get behind it. And we said, well, what is the best way to understand that? And I said, it is to study play. And there was no science of play because people said it was too chancy, idiosyncratic. You could never bring it into the laboratory. It happens here and there, but you can't control it. Well, it turned out that with rats, who are not good for psychological pain, they're wonderful for play. And that's probably why they're wonderful, because they can live alone without much pain, and when you put them together, they're so hungry for play. The young ones begin to rough and tumble and run around, and you can study it as systematically as anything in science. And we were shocked how clear it was. So we studied it and developed measures for it, studied the chemistries that control it, studied the brain areas that mediate it, the sensory systems. The most important sensory system in a rat is touch. Mm-hmm. Probably the same as our little children. To have play without touch. You know, if you play with your 2-year-old, you better pick it up and throw it and be physical. They love it. That's the best play. So I think touch is the source of play. Hearing is a form of touch. And recognizing that hearing is a form of touch, a specialized touch. And when we look at our children, that's when they're laughing more than any other time. So if you ask, where is human laughter the highest in the natural world? Forget about the artificial comedy shows and stuff. There's lots of laughter there. There we're tickling with words, but in real play, we're actually tickling the body. We're touching it, we're chasing it, and children love it. And we could study it in animals, and we could study the brain mechanisms, and finally there's many other people studying it. It took a long time. I think the first many years we were completely alone, and we were not even allowed to use the word play. The colleagues said this is unacceptable anthropomorphism, giving animals human feelings. And we said, well, what do you want us to call it? You know, and play is P-L-A-Y, and just for fun we called it the prominent ludic activities of youth. PLAY. So we said, now we have a scientific term, huh? We capitalize it. Oh, you have to play these games because, we have a long and illustrious, but in a certain way, a sad history in psychology, because the academic form of it left the organism outside the door and brought our preconceived notions of mind and behavior and learning in, but left the organism outside. And there were a group of Europeans that wanted to bring the organism in, and they were called ethologists. Konrad Lorenz, Nico Tinbergen, von Frisch with bee dances. They brought the organism back, but they still left the emotions out. Because they were just studying the natural behaviors, and the natural behaviors are the organism. So studying those was valuable, but Nico Tinbergen in his famous book, The Study of Instinct, 1954, on page 4 says, we cannot go into the subjective realm. We cannot talk about emotional feelings. And they were being honest because they were just studying the surface. To talk about emotional feelings scientifically in animals, you have to do brain research. You have no option. And so we, on studying play, we were already neuroscientists, and that was the most interesting thing for us was, is this a basic emotion? And just putting animals together and they play freely does not make it a primary process. We have to be able to show there's a circuitry for it, that there are chemical controls for it, that evolution provided. That makes it a primary process. One of the first questions we asked was, do you need the upper brain in order to play?
Okay.
It's a straightforward experiment. It's not pretty necessarily, but it's not ugly either. We took young rats, 3 days of age, and we surgically took away the whole neocortex. And the mother takes wonderful care of the babies. The babies drink and eat, and they look normal, and they grow up, and they look normal. They look so normal, they look super normal. I'm not just saying this. I once had a neuroscience practicum where I had 16 students learning brain and behavior. And I told the students that you're going to learn about the brain and behavior in this course. And the very last experiment in class, I will give you 2 animals that I am preparing this week for you. You will have one animal that's missing 25% of its brain. But it's the most recent upper part of the brain, the neocortex. The other animal will have had surgery, but the brain is intact. In that last meeting, your only job is to tell me who is missing 25% of the brain. Of the 16, 12 selected the decorticate as the normal animal. Which statistically is a mistake in the wrong direction. Well, it is a mistake, a significant mistake. One could say they didn't learn anything about what I was teaching them, but of course I hadn't told them that this is exactly what you should expect, because the emotions are lower down. The higher brain regulates and controls what the emotions are saying, and now you have animals that are very active, they're interesting, they're doing lots of things. The normal animals were sitting in a corner a little scared what was going to happen, and sitting in a corner not doing anything looks a little stupid. So this is what the upper brain can do. It can immobilize the emotions.
Just a disclosure, Walter Freeman wasn't right with his lobotomy style.
You can't translate everything from rats into humans. We humans have such a large upper brain, and we become dependent on it in so many ways. Language, culture, all the complex things we do. But we do know that humans that are born without an upper brain are human beings. They behave emotionally very directly because they don't have thoughts about their emotions. That's what the upper brain does. So, but in order for these children to grow up to be humans, they have to be brought up in families. If you leave them in a hospital by themselves, they don't learn anything and they become very wretched. They don't behave, they show stereotype behavior. But the point is that the cortex is not needed to be emotionally human. The cortex is needed to symbolize all the things that we symbolize because it makes our life more effective. The symbolic capacities have given us language, but language is learned. There is no instinct for language. There's an instinct to communicate. And the most important communications are emotional communications. So language is based initially upon emotional gesture. Scared. And it's also based upon the sounds of emotion. The sounds of emotion are universal across animals. I can tell when another animal is happy. Even rats with their happy sounds. And we know that those feel good because when we tickle the happy sound circuit, the animal loves it. It wants to listen to it. It wants to turn it on. So we know it's a good feeling. So a mother brings language out of the child by singing to the child. And the child is engaged by the emotional sounds, the up and down of motherese. And the mother begins to point to things in the world. And like St. Augustine said, initially I knew nothing. But then I learned that people made sounds that indicated objects in the world. And I learned to use these sounds. The notion that we have a language instinct is a very dangerous one. We have the brain capacity to develop language. We certainly have a desire to communicate our emotions, but those are the foundations of language. Every language is learned. The cortex even learns how to see, because Karyanga Sur at MIT did experiments with mice where he eliminated the visual cortex in utero before birth and asked, will these mice see normally? And the answer was yes. The lower parts of the brain wanted to go into the closest cortex, and they developed visual competence up there. I think language is similar. We do not yet have any genetic understanding of language. Language is clearly a cortical function in the left hemisphere. But if a child has epilepsy here and they take the left hemisphere away, it develops perfectly well in the right hemisphere. I suspect that if at birth a child lost Wernicke's area, they would still develop some linguistic competence. We don't know. Those experiments, those accidents of nature have not occurred. But people that talk about language instinct are talking about a probability that they see in their minds as opposed to pointing to data that is scientific. And I would rather be a skeptic about the specialization of the higher brain. Even though the lower brain, these emotions are built in genetically, they still become refined by experience. So they get stronger or weaker depending upon the emotional life you have. The higher part of the brain develops its competence completely by learning. It is constructed by culture and the world. And that's why we have such conflicts among different cultures and different belief systems. Because we bring up our children with our stories. And they're all stories. But we begin to believe our stories. And, this deep belief system that develops in our species has become a source of conflict for centuries. It continues to be a source of conflict. And it would be wonderful if we humans realize that underneath it, we are very similar at an emotional level, and that the upper brain is passed down to us by our culture. The way we look at the world. So an Eskimo will have 20 words for types of snow, because that's their world. A person that has never seen green, and then all of a sudden is given green, probably will not see green. So much of the upper brain, the upper mind is constructed through learning, that there is plenty of room for all kinds of constructivism. Sometimes people criticize me that I'm a determinist. You think things are, genetically coded. I'm just reading the brain the way it's presented to me by nature. When emotional systems are in the same places in the brain in very different species and have the same chemistries, the possibility that that is learned is very remote. We cannot come into the world without tools for living. If you put us into the world as a blank slate, we will not survive. We have to have tools. And those tools have to tell us what supports our life and what can take away from our life. And that's what the emotions are. And the fact that psychology during the behaviorist era said we never even talk about them. Can you imagine that scientists would close the book on talking about things, talking about the possible nature of the world? But this is what happened historically. We have brilliant men of extreme arrogance telling us what we could talk about and what we couldn't talk about. I was trained in that tradition, and in my mind I said, this is not right. These are important questions, and we are denying some of the most important phenomena. So even to this day, most psychologists have left the organism outside the door, and they study the concepts that they have. And when I say the organism is still outside the door, it's because we're not ethologists. Ethologists said, let us study animals in the real world. If we do that, then all of a sudden, the places where we only had words become real things. And you might ask, what are the words in traditional psychology that reflect the organism but are not studied by psychologists? And the answer would be the two words necessary for learning. The two words in scientific language are unconditioned stimuli. Tastes good, tastes bad, hurts, all those things. We use the word, but we don't study the underlying process. The even more important word is unconditioned response. Mm-hmm. The unconditioned response is seen just as a knee-jerk reflex. Mm-hmm. That's the response. But the emotions are not like that. The emotions are complex, unconditioned responses that the organism is built around. So we left the unconditioned emotional response outside, not welcome. And to this day, it's very hard to bring it in. Mm. The main goal of affective neuroscience is to bring the organism back into the room, to discuss it realistically, to see that we are organisms. Yes, we're the smartest ones in town, but we share the tools for living. And if we don't really understand the tools for living, if we just focus on learning and memory, the way Kandel does, the way most learning psychologists do, and we don't spend time on the emotional unconditioned responses, we will not understand who we are. So that's the goal of affective neuroscience, to allow the other animals to teach us who we are.
Great final word. Professor Panksepp, thank you for talking to us.
I appreciate talking to you.